Hi guys, so this is homework number 3, Q3. So I'm just gonna get right into it. So this is pretty much a picture of what we have going on here. So the speakers are root 7 meters away from the wall. We have an observer here who moves over 1 meter. At his original position, he's experiencing perfect destructive interference. And when he moves over 1 meter, he's experiencing perfect constructive interference. This problem is concerned with the constructive interference, so I'm just gonna get right into it. So at this point right here, when the speakers are emitting their sound waves, the path that it takes that the observer observes is kind of like this from each speaker. This and like this. This is essentially just the path that the sound waves take that the observer observes. And so we have these two lengths right here to begin with. Next thing that we do know is that from any point from the wall to the speakers, it gives us a value of root 7 meters. So I can say that from this distance to this distance, it's gonna be that line right there. And the last thing that we know is that the difference between the distance of the speakers is 4 meters. So then I can just kind of draw that line right there. And we know that that distance is 4 meters. So essentially, now we have two right triangles, and what we're concerned with now is the difference, the change in R. So we can just label these arbitrarily, R1 and R2. And now we can kind of just solve for this. So we see here that like roughly like the midpoint between these two is like right here. So I would say this length right here is 2. I would say this is 1 and this is 1. So we have 2 meters, we have 1 meter, and we have another 1 meter right there. And we have also this right here. And these are essentially just two right triangles that we can solve using the Pythagorean theorem to get R1 and R2, which will then get us the change in R. So for R1, we have R1 equals, or R1 squared equals 2 plus 1 is 3. So we have 3 squared plus root 7 squared. Root 7 squared. So that's R1, and we can just solve for R1 now. We can root both of these sides. We get R1 equals root 9 plus 7, which equals root 16, which equals 4. So now we have R1, which is equal to 4. Now we can get to R2. So same procedure, Pythagorean theorem. It's going to be R2 squared equals this distance to this distance is 1. So we have 1 squared plus this is root 7 plus root 7 squared. And we can just square root that whole thing. So we have R2 equals 1 plus 7. We have R2 equals root 8. So we solve for R1 and R2, and now we just need to solve for the change in R. The change in R is just R1 minus R2. So that's just going to be equal to 4 minus root 8, and that is ultimately 1.2. And I apologize, the units are meters, of course, because the units all there were meters. So you have change in R equals 1.2 meters. So that's the first step. And now the next step is kind of trying to find an equation that relates this change in R to wavelength, which will hopefully help us get to frequency, because that's our like end goal. We're trying to get to frequency, but we need to take those like little steps. So if you guys remember, there are a couple of equations we got here for phase. So this right here is going to be phase is equal to 2 pi times change in R over the wavelength. So that's one equation. So immediately, like when you look at this equation, we kind of have an issue because we don't have all the necessary variables. We're trying to solve for wavelength. We have the change in R, but we don't have the phase change. So additionally, another equation that this is like analogous to is also change in phase is equal to m times 2 pi. So yeah, these are our separate equations right there, and they're equivalent. And oh, I'm sorry, I messed up on this one right here. It's actually plus also that right there. My bad. But yeah, so these are 2 equations right there, and they're both equivalent. So now looking at these equations, we can kind of like knock out variables that we already know. So we know that the change in R is, we got 1.2 meters, right? We also know that m is equal to 0. Essentially, m is equal to 0 because after the observer moves, you get your first instance of constructive interference, and we know that after that first instance, m is equal to 0. Additionally, like if you go forward, like if you get your second instance, m is equal to 1. That's just something that we know. So we also know that m is equal to 0, and because the speakers are out of phase, that's something that they address like in the beginning of the problem. We also know that this phi naught is equal to pi. So we have all of our variables here to pretty much solve for that wavelength. So what we're going to do is set these equal to each other. So it's essentially just going to be 2 pi times this equals m times 2 pi. And now we're just going to plug and chug essentially. So we have 2 pi times 1.2 meters over wavelength plus pi equals 0 times 2 pi. 0 times 2 pi, that's just 0, so 2 pi times 1.2 meters plus pi equals 0. We can move that pi over. So now we're going to have 2 pi times 1.2 meters over the wavelength equals negative pi. And now we can just cancel out these pi's right here. You can just essentially divide each side by pi. Cross that out right there. Now we have 2 times 1.2 equal to the wavelength, which equals this side's negative 1. So now we have this side, which is equal to negative 1. But the wavelength obviously cannot be a negative, so this is just an arbitrary side, like that negative, so we can kind of just ignore it essentially. So next thing that we do is we have 2.4 over the wavelength equals 1, and rearranging that, you get the wavelength is equal to 2.4 meters. So we've essentially gone from going to R to finding the wavelength, and the last thing that we have to do now is relate the wavelength to the frequency, and then we'll be good. So the last part, we're going to use this relationship right here. So distance equals rate times time, right? Pretty simple. applying that to waves, we have wavelength equals velocity times times period. So we have this relationship. So we have V over F. Now we just need to rearrange this to get F over here. And so we're just going to have F equals velocity over wavelength. And at the beginning of the problem, they give us velocity as 360 meters per second. So we have V equals 360 meters per second. And we also have our wavelength, which is 2.4 meters, right? And so we can just plug and chug with 360 meters a second over 2.4 meters. And that gets us our final value of 150 hertz, which is our final answer. So yeah, as you can see, start off with change in R. We found our wavelength and we related that back to frequency, and we ended up with 150 hertz. And yeah, I hope that helps.